US Physics Olympiad, year 2011, USAPHO Semifinal Exam. Problem B2. Solution for this problem you can find below this video in the reference of the description. A particle is constrained to move on the inner surface of a frictionless parabolic ball whose cross-section has equation z equal kr square. Particle begins at height z0 above the bottom of the ball with a horizontal velocity v0 along the surface of the ball. The acceleration due to gravity is g. Question A. For a particular value of horizontal velocity v0, which we will name vh, the particle moves in a horizontal circle. What is vh in terms of g, z0, and or k? Solution. Suppose that a particle moving on a distance r from axis z and on height z. In that case, we can write equations for motion. On this height, we have normal force, and we have slope of this curve with angle theta. So we can write equations for this motion. In vertical, we have this equation that mg must be equalized by normal force multiplied by cosine theta. In horizontal, we have normal force multiplied by sine theta, create a centripetal force to move by circle, which is this equation. We have mv square over r equal normal force multiplied by sine theta. Now we can divide this equation by this equation, and we have tangent theta equal this expression v square over gr. But from other hand, we can find this tangent by taking first derivative from z by r. That will be tangent theta equal 2kr. And now we can equalize these two tangents, and we get v square equal 2gk r square. But kr square, that's z0. So we have v square equal 2g z0. And this is our answer for velocity vh. That will be vh equal square root from 2g z0. That's the answer for question A. Question B. Suppose that the initial horizontal velocity is now v0 greater than vh. What is the maximum height reached by the particle in terms of v0, z0, g, and or k? Solution. In this part, we can use energy conservation and angular momentum conservation, because there are no forces which can change the angular momentum. So first, let's write equation for energy conservation. In point height z0, we have mg z0 plus 1/2 mv0 square equal same thing in point z. So potential energy in point z, which is mgz, plus kinetic energy in point z, which is 1/2 mv square. From other point, we have angular momentum conservation. In lowest and the highest points, we have velocity has only horizontal part, no vertical part. And In the lowest point we have mv0 multiplied by r, which is square root from z0 over k. That's equal to mvr in the highest point. Now we can cancel masses in both equations. We can square a second equation and we will get next equations. This is energy conservation and this is angular momentum conservation. So now we can rewrite it in form of this one, and we can express v square from this equation. So in the highest point v square equals z0 over z multiplied by v0 square. And we can put this expression to this equation. That will give us a quadratic equation to z. And the solution for this equation we can write here. That will be this equation. If we can see carefully, this is square root from this expression. That's exactly square root from perfect square, which is a v0 square minus 2g0 square. And we can write two roots for this solution. That will be z1 is z0, which is trivial, and the other z2 equal v0 square over 2g. And because v0 greater than vh, so we have z2 greater than z0. That's the solution for question B. Question C. Suppose that the particle now begins at height z0 above the bottom of the ball with the initial velocity v0 equal 0. First question. Assuming that z0 is small enough so that the motion can be approximated as a simple harmonic, find the period of the motion in terms any or all of the masses of the particle m, g, z0 and or k. Solution. Because z0 is very small, we can assume that angles are very small. So correct assumption for this motion will be that angle theta approximately equals sine theta, approximately equal tangent theta, and tangent theta equal dz over dr, which is 2kr, and cosine theta approximately equal 1. Now let's write equation for tangential acceleration. Tangential acceleration we can find from this formula. Also we have centripetal acceleration, but because motion is very small, we can neglect centripetal acceleration. And tangential acceleration we can convert to radial acceleration. And for radial acceleration we have this equation. It's equal tangential acceleration multiplied by cosine theta, which is negative g sine theta cosine theta. And because angles are very small, cosine is about 1, sine theta is about theta, and finally we will get negative g theta, but theta equal 2kr. So we have equation AR equal negative 2kgr, which is corresponding to oscillation with omega equal square roots from 2kg. And from here we can find what is the period. Period will be 2 pi over square roots from 2kg. So that's the answer for part C, question 1. Part C, question 2. Assuming that z0 is not small, will the actual period of motion be greater than, less than, or equal to your simple harmonic approximation above. You need not calculate the new value explicitly, but you should show some work to define your answer. Solution. We already found that the radial acceleration equals tangential acceleration multiplied by cosine theta, which is equal to negative g sine theta cosine theta. But we found that only in case of AR equal negative g tangent theta, which is equal to negative 2kgr, we have a perfect simple harmonic motion. But in our case, we always have sine theta cosine theta less than tangent theta. It means that in any point radial acceleration less than acceleration for simple harmonic motion. It means that period will be greater than for simple harmonic motion. That's the solution.